More simplification with radicals, this time radicals that contain fractions. So I look up here and I have square root of 1/2 and I want to simplify this. It's not in simplified form because I have a fraction underneath my square root. So what I do is divide that up into two separate square roots, square root 1 over square root 2. That's property 2 for square roots. Now square root of 1 is 1, so I have 1 over square root 2. Now this is not in simplified form because I have a square root in the denominator. So to take care of that, I do what's called rationalizing the denominator. I multiply by square root 2 over square root 2. This is the number 1, so multiplying this by 1 won't change the value of this, but square root 2 times square root 2 is the square root of 4, which is just simply the number 2. So I multiply on top 1 times square root 2 and I get square root 2. On the bottom, square root 2 times square root 2 is the square root of 4, which is just 2. So that expression is in simplified form because there's no perfect squares that divide what's under the radical here. There's no fractions under this radical, and there's no radicals in the denominator. So that's simplified form for radicals. Next problem, 10 square root 15 over 5 square root 3. I could do the same type of thing, but look, this is the same as 10 over 5 times square root 15 over square root 3. If I want to look at this as a multiplication problem with fractions in reverse. Now 10 divided by 5 is 2. Square root 15 over square root 3 is the square root of 15 over 3. I can use that property 2 for radicals in that direction. That's 2. Square root 15 divided by 3 is 5. So I can multiply and divide numbers that are outside the radical, and I can multiply and divide numbers that are inside the radical. Sometimes it's convenient to go backwards like this and simplify rather than trying to rationalize that denominator. But the other way works also. Here's another problem. Another fraction. I'll separate this into two separate expressions, square root of 16a to the 4th over square root of 5. That's property 2 for radicals. Positive square root of 16a to the 4th is 4a squared, assuming that a is a positive number, over square root 5. I want to rationalize this denominator, so I multiply by square root 5 over square root 5. And that gives me, in the numerator, 4a squared, square root 5. And in the denominator, square root 5 times square root 5, which is square root 25, which is just simply 5. So there's the simplified version of that. I know it's in simplified form because there's no perfect squares that divide this. There's no fractions under this radical, and there's no radicals in the denominator. Therefore, it must be in simplified form. One last problem. How about a cube root of 1/2? Well, let's see. Use property 2, cube root 1 over cube root 2. The cube root of 1 is just 1, so I have 1 over cube root 2. Now, this is not in simplified form because I have a square or a cube root in the denominator. I want to get rid of this, so I need to multiply numerator and denominator by some cube root. And what I multiply by has to end up in the denominator with the cube root of a perfect cube. So what can I multiply cube root 2 by in order to get the cube root of a perfect cube? The answer is cube root 4. Now, in the numerator, I have 1 times cube root 4, which is cube root 4. In the denominator, I have cube root 2 times cube root 4, which is the cube root of 8, which is just the number 2. So between here and here, I have cube root of 2 times 4, which is cube root of 8, and the cube root of 8 is just 2. So that's how the cube root of 1/2 looks when it's in simplified form for radicals. Now there's a couple of examples in the book like this. You might want to read through those too. Also, and then come back and look at the video of this one right here to see why it is we multiply by cube root 4 here in order to get just a 2 in the denominator.